Hello everyone, and welcome to TESCO and Sumatec's PIM testing webinar. I'm Terry Maxwell, Product Manager with TESCO's Test Equipment Business Unit. We have seen a great deal of interest in the cellular industry for this topic and are very excited to have all of you joining us today. We ask you to submit any questions you may have at any time during this webinar via the Q&A chat box. This Q&A chat box can be found on the left side of your screen when you're not in the full screen mode. We will address these questions at the end of the presentation material. For those of you experiencing technical issues or are not currently online, you may view the recorded version of this webinar at a later time. TESCO is a value-added provider of product solutions needed to design, build, run, maintain, and use wireless systems. A few of these solutions include network infrastructure products, mobile devices and accessories, installation and supplies, and last but not least, test equipment. TESCO has a dedicated test equipment business unit which represents a large number of leading test equipment vendors. And TESCO is the sole distributor for Sumatec's PIM testing solutions. And at this time, I'd like to hand this webinar over to Tom Bell with Sumatec, the recognized leader in PIM testing equipment.
All right, thank you, Terry. I appreciate that. Starting off, who is Sumatec Instruments? Sumatec Instruments was founded in 1996 in Denver, Colorado. We're part of the Smiths Group, which is a $4 billion consolidation, primarily of high-tech companies. Sumatec's primary business focus has been on delivering passive intermodulation test solutions for the last 14 years. We have more than 800 factory PIM test sets in service worldwide with RF equipment manufacturers, and we delivered more than 1,200 portable PIM test sets worldwide to installers, third-party inspectors, and network operators. But getting right into the meat of the presentation, what is passive intermodulation? The simplest definition is that PIM is interference. It's noise that is generated by your transmit signals at a cell site interacting with materials in the RF path. And if I break that down into the key components of that statement, first and foremost, you have to have multiple signals. And those multiple signals all need to be at high power. If those multiple high-powered signals go across what I'm going to call a nonlinear junction, or anything in the system that either a metal-to-metal contact or a material that acts like a diode, it actually forms a mixer, which is creating new frequencies that you never intended to create in the process. Now, the last part of that statement is important, saying it's in the RF path, because what it says is that these nonlinear junctions may be beyond the antenna. It's not just the feed system at the site or the direct components in the system, but you need to be concerned also about metal objects or junctions that may be close to the radiating surface of the antenna. But at the end of the day, PIM is reduced BTS coverage and capacity. That if PIM is falling in the receive band of the system, it's going to cause an elevated noise floor, which is going to result in dropped calls, reduced data rates, blocking, etc. What we typically find at cell sites is that the majority of the problems we're finding are related to these bad metal-to-metal contacts, whether it's loose RF connectors, poorly prepared cable terminations, improperly mated parts, cracked joints, metal chips and shavings, loose mechanical fasteners, or overlapping metal surfaces like you might find on a flashing at a roof vent. By far and away, this is the vast majority of the problems we find and fix using passive intermodulation test equipment. To a lesser degree, we see ferromagnetic materials, and ferromagnetic means any material that holds magnetization. It's nonlinear because the relationship between the magnetization level and the applied magnetic field is nonlinear, and so therefore it's impacting the alternating magnetic field of the system, which is causing PIM. Looking at the pictures to the right, it's pretty obvious when you look at the RF preparation on this feed cable There's no manufacturer's specifications or directions that say to leave large hanging burrs or drag the dielectric into dirt. This is the type of thing that we find, though, that standard sweep testing just doesn't find these types of subtle defects. The picture at the lower left is metal flakes that were shaken out of a connector that we just assembled that was showing PIM problems. And the one on the bottom right is showing metal flashing for weatherproofing on the edge of a building parapet. And that if antennas are pushed back far enough away from the edge of the building, these metal surfaces can come into play and be sources of passive intermodulation. Now, the result is that if I have multiple frequencies transmitting through a system and we come across one of these nonlinear junctions, I'm going to generate all these other frequencies. These are the frequencies that we call passive intermodulation. They are all mathematical combinations of the carrier frequencies that we're starting with. In the picture shown, F1 and F2 would represent downlink frequencies at a cell site, and all these other PIM spikes are the frequencies that are generated by those two tones. Now, the important thing here is that you never intended to create any of these frequencies. They're all interference. From a definitions standpoint, we describe these frequencies based on the mathematical combinations. So, for instance, if I have a fifth order intermod problem, or IM3, it is formed by 3 times frequency 1 minus 2 times frequency 2. Likewise, a seventh order IM is one that would be 4 times frequency 1 minus 3 times frequency 2. So as you can see, the sum of the multipliers is how we describe the order of the PIM problem. Getting into how the test equipment works, we start off by transmitting these two frequencies. So we generate them within the equipment by having two sources. We go through an internal amplifiers, and we filter those frequencies so they're very, very narrow band in bandwidth. We combine the two frequencies together, and then we send them out the system. We transmit the tones at 20 watts each. That's an industry standard for PIM testing. If there are any nonlinear junctions anywhere on the line, they're going to get excited by those two input tones that we've put in. The PIM that's generated, it acts like a point source radiator, which means that not only is the passive intermodulation going to follow the transmit tones out the antenna, but it's also going to go right back towards the receiver. Inside of our unit, the first component it addresses is a duplexer, which is going to separate out any of the PIM problems or PIM frequencies that are falling within the receive band of the system. It then pushes them to a filter where we very narrowly focus around the specific PIM order we're trying to measure. Then we amplify it and display the result. Typical site-level pass-fail limits for PIM testing are minus 140 dBc, or a minus 97 in dBm terms for new construction, or minus 130 dBc, which is a minus 87 dBm for legacy sites. The higher level for acceptable level for legacy sites is generally a trade-off between dollars versus dBs. You know, ideally you'd like everything to be at a better than a minus 140 dBc. But for the many, many problems you typically find at older sites, like I said, it's a trade-off between how much time do you want to spend fixing them versus how long is it going to take. The test frequencies that we choose are ones that are chosen so that they're going to cause an IM3 frequency to fall within the receive band of the system. IM3 is the industry standard for PIM testing. So we need to select two frequencies on the transmit side that are going to result in an IM3 falling in the receive band. In just about every system out there, you need to choose at least one frequency that's going to fall outside of your licensed spectrum block. And to do this in a way that doesn't cause interference, we typically choose a guard band frequency for either one or both of the transmitting frequencies. Guard band frequencies are frequencies basically at the barrier between spectrum holders, where in this case, looking at the PCS spectrum holder in block A is going to stop short of the actual barrier, as is spectrum block holder D. And the reason is that the RF signals tend to spill over. You can't have a perfect cutoff at your transmit frequencies. So when we're doing PIM testing, we center our transmit tones right on that barrier between the two frequencies and take advantage of that guard band so that we're limiting interference that could potentially fall on either of the operators. The chart below shows a list of the guard band frequencies for the cellular bands in the United States. Now, when you're doing PIM testing, we use what's called a tapping test in order to dynamically stress the system to find the location of the PIM faults. So what we do is we lightly tap on the junctions, and if there is a PIM problem, the magnitude of the PIM will generally spike, allowing us to find and fix that problem. Now, this dynamic testing is important not only in helping to find the static problems, but also it ensures that the feed system is robust. As you can see from the example above, that when we were tapping on the system, if I can get the marker to work, when we're tapping on the system in good joints, we see very little response. But as soon as we get to a bad joint and start tapping on it, we see very large swings, as much as 20 or 30 dB changes in the magnitude of the PIM. So if we have a system that when I'm measuring it static and it's passing, you want to make sure there's not elements on that line that are going to eventually get into a position that they could cause PIM based on either thermal expansion caused by just daily changes in temperature or by wind loading or vibration at the site. Now, so far, everything I've talked to you about is not new. You know, PIM testing has been around by more than 14 years, or longer than that. 14 years is how long Sumatech has been in business providing packaged solutions to be able to sell to RF equipment manufacturers. In factory PIM testing reveals problems with raw materials, plating defects, loose fasteners, workmanships, and parts tolerance problems. So the RF equipment manufacturing industry has been learning from how to make PIM-free products for a very, very long time. What is new is the fact that we've now carried this technology into the cell sites. We now have portable equipment that allows us to do system-level PIM testing in the cell. Now, what this is going to find is not only the workmanship issues, but also it'll identify components that may have been damaged during installation or components that were damaged in transit. And what we're finding is the learning that the RF equipment manufacturers did 10 years ago in how to make PIM-free solutions. We're now just now really addressing that in the cell site space. Historically, sweep testing has really been the only method available to us to measure installation quality. The way that a sweep test works is that we transmit a low-powered signal into the system, and we measure the magnitude of the reflected energy at that frequency. We then step the frequency across the operating range of that site, and we plot the reflected power versus transmitted power on what is a very typical sweep test plot. Now, sweep testing is very, very effective at finding many defects. It'll find things like kinked jumpers, crushed coax, poorly matched components like antennas or filters or such. It's looking for impedance mismatches. Anytime that there's a large impedance mismatch either at a junction or at a component, it's going to cause a reflection and it's going to measure that reflection. Now, what PIM testing can't do, or excuse me, what sweep testing cannot do is it's not going to identify PIM problems. By definition, by sweep testing, I'm transmitting a single frequency at a time, and I'm transmitting that frequency at very, very low power. So by going back to that original slide's definition of PIM, I'm not going to generate PIM by doing a sweep test. To illustrate this, we have done testing at a large number of sites with operators while we're demonstrating the value of PIM testing. And so this data was collected over 100 feed lines with 19 operators in 11 different countries. And as you can see, we found many, many PIM problems in these sites and relatively few VSWR problems. And what's showing is that, approximately 95% of the sites we tested were good from a sweep test standpoint. It's really not a surprise. Those sites were all qualified or commissioned using sweep test equipment. And so therefore, they were not seeing any PIM problems that were created or generated at the sites. There's an old adage that says tell me how you're going to measure me, and I'll show you how I'm going to perform. And this is a great example of it. The tools that are available in the industry for certifying quality just really don't show PIM problems. You need to have equipment that's really designed specifically for that purpose. Now, some of the problems that we found, the vast majority of them were workmanship-related issues in metal-to-metal connections within either the RF jumpers or within the feed cables. Now, if you look at the totals here, you'll notice pretty quickly it totals to more than 100%. And what that means is that many of the lines that we tested had more than one problem present on that line. Number 1 and number 2 are the feed cables and the jumpers, and number 3 is antennas. Antennas are actually a special kind of a device. You need to understand that in the cable system, all the RF fields are contained. And so therefore, you're really limited to PIM problems being incurred at the ground connections or the semiconductor connections. But with antennas, by definition, they're designed to illuminate, which means that every single nut, screw, bolt, washer, what have you, inside the antenna is going to be illuminated by high RF power, which means that every single one of those joints has to be perfect. So you need to be especially careful when handling antennas at the cell site or getting them to the cell site to make sure that just your transportation or installation doesn't hit the antenna in a way to cause one of those connections to become loose and then become a passive intermodulation source. The other passive devices that we've seen have been things like diplexing filters, surge protectors, bias tees, etc. Now, most of the sites we tested and did the improvement of the PIM or fixed the PIM problems did show fairly impressive improvements in the KPIs for those sites. And I'll show you some examples. How can you recognize PIM problems in your site? Well, first and foremost, looking at your drop call rate is probably one of the most telling ways of seeing if you've got a PIM problem. PIM is going to reduce the signal-to-noise ratio. And so basically effectively reducing the cell size, which is going to cause coverage gaps, which is generally going to cause drop calls. The example here below is one where a new frequency or a new operator was added to a DAS system. And you can see that the drop call rate was running along, it looks like approximately 1%, sometimes spiking higher based on whatever issues were happening. But as soon as the new operator with new frequencies was added into that system, it threw a third-order intermod product directly into the receive band of one of the existing operators. And this is data showing what the results were. So this dramatic change in drop call rate is indicative of the fact that new frequencies were added on top of an existing passive intermodulation problem. Data from a GSM operator, they were looking at specifically interference on idle channels. They had high interference levels prior to us coming in and fixing the PIM problem. And then you can see that on the date that we fixed the PIM problems, the interference on idle channels dropped dramatically. What's also interesting is if you look at the area of the light blue regions under the curve, that's representative of successful traffic channel allocations, which is a measure of the number of users on that system. And as you can see, not only did we reduce the interference in the system, but we see what you would expect, which is that the total traffic being carried on those sectors actually increased as a result of fixing these noise-related problems in the system. A similar metric on a CDMA channel would be looking at the access channel utilization. In this particular example, you can see anytime the color is anything other than the orange or the yellow, it means that the access channel is showing up as being occupied. When it reaches the red that's shown, it means that it's 100% occupied, meaning that no additional users are allowed to access that particular channel or at that particular site. So after fixing the PIM problems, the access channelization was dramatically improved, which means that the majority of this traffic that the system was seeing was actually caused by passive intermodulation. This is particularly troublesome because this type of a metric never shows up on your drop call rate. These users were trying to access the system but were never able to access, and so since they never accessed, they never show up as a drop. And so this is what you might call a silent call killer. Probably one of the most common methods or ways to tell if you have PIM in your network is to look at the RSSI, or Received Signal Strength Indication. Most systems have some form of a diversity alarm that says if there's an imbalance between the average receive level between the main and the diversity branch, it's going to send an alarm saying, hey, there's something wrong with this sector, go take a look at it. Now, as you can see here, this is a classic example where the main branch is being impacted by a PIM problem and the diversity branch is not. This is a key indication that there's an internal problem in the system. If there was an external interferer present, then you would expect whatever the noise was to be impacting both branches equally. And as you can see in this case, once again, once the PIM problems were fixed at the site, we have even tracking on the receive levels between both the transmit and the receive. How severe your PIM problem is going to depend on primarily three things. Number one, how high is your transmit power? PIM is very, very power dependent. For IM3, for example, which is what we're measuring in the system, for every 1 dB increase in transmit power, the PIM level for any given defect is going to increase by 3 dB. So higher transmit powers have very high impact on the magnitude of the IM that's generated. Now, this is going to affect not only IM3, but obviously all the other IM products that are generated. The degree of nonlinearity of the problem. The higher the nonlinearity, the higher the PIM that's going to be generated by that problem. Just as an example, if we're talking about a loose connection at a cell site, if it's tight but just not torqued correctly, that might cause a certain amount of passive intermod, compared to if it's just barely connecting with two threads of engagement, that may be a very severe PIM source. And then, as I talked about previously, frequency combinations play a big impact in how severe the problem is on your system. The more operating bands that I have sharing on a particular feeder, the higher probability that PIM is going to fall into my own receive band. All of the slides that we've shown so far have been, describing passive intermodulation, are taking a very classic picture of showing two very fixed narrow tones and the specific tones that are created by those two frequencies. Well, in systems like DAS systems, where I may have multiple operators at multiple frequency bands, I now get many, many different combinations of frequencies. Now, we are using third-order intermod as a method to clean up these sites, but you need to understand that it could be a third-order intermod could be the fundamental combination of three different frequencies. So, once again, we use passive intermodulation testing, and we use two specific tones in order to find and eliminate nonlinear junctions. But once you get into the real-world system and put many, many frequency combinations on a common feeder, you now end up exciting many different problems. It also turns out that the bandwidth of the signals that are being transmitted through the system impact the severity of the problem as well. So, in an example above, and we've drawn on here the representative bandwidth of the PIM frequencies, or the PIM signals. An IM3 is going to be 3 times the bandwidth of the fundamental frequencies that are being transmitted. IM5 is 5 times, IM7 7 times, IM9 9 times, etc. So eventually you get to the point when you get out to IM11 or IM15 where if you are an operator in that band, you don't see it as an individual spike. You just see a general noise rise across the entire operating band for that system. Also, the spacing between the receive band and the transmit band are going to greatly impact how badly PIM is going to impact your system. If I am a licensed band in the United States, the FCC has done a pretty good job of trying to make sure that IM3 and IM5 don't naturally fall within your licensed receive band. However, if I end up doing things like mixing AWS and PCS together onto a common feeder, now I'm going to start seeing IM3 actually falling in directly into my own receive band. So these combinations of things are the things that are all resulting in how severe the actual PIM problem is in your band. Now, something that's also important to note I show in this picture above, IM9, IM7, and mentioned that that's kind of a typical frequency spacing allocation within the United States. It doesn't mean that you don't have to worry about passive intermodulation. This is an example using the spectrum analyzer mode of our IQA analyzer. And what we do here is we choose two transmit frequencies. And in this particular case, we've chosen two frequencies that represent the A block of the PCS band. So these are actually two A block PCS transmit frequencies. And on receiving, we sweep the entire PCS receive band. So we're not just having a fixed frequency around IM3 or IM5. We are now sweeping this receiver across the whole band and seeing all products that are created as a result of the passive intermodulation problems on this particular site. And as you can see here, IM3 in this particular case, if I choose two A block PCS frequencies, IM3 doesn't even fall within the PCS receive band. But in this particular case, which is the sample over to the right, we had intentionally injected one metal flake inside of a connector in order to generate the result shown. And so this one metal flake was causing a third order intermod of a minus 60 dBm. And looking at those higher order products, 5th, 7th, 9th, and 11th, going all the way down to 11th order, it created a minus 93 dBm signal directly in the A band receive block. So this is an example of an A block PCS, two A block PCS transmit frequencies generating a neg 93 dBm signal directly in to the A block receive, caused by something just as simple as a metal flake inside the connector. And a neg 93 signal, that's going to compete for your receiver. That would show up to the system as a fairly high user. And once again, IM11 means that whatever the bandwidth was of those two transmit frequencies, this neg 93 dBm signal is going to be 11 times the bandwidth of that original signal, which means that you're going to do significant blocking within your own receive band if you have problems like this. Now, something that's important to note is as well that by fixing IM3, we also fix those higher order modes. So that's why we use IM3 testing. It's the industry standard for passive intermodulation. All the components from your manufacturers have been tested to IM3. We use the same thing in the cell site, even if IM3 doesn't fall specifically in your band. But by fixing IM3, you are fixing the products that do fall within your band. Okay, let's go over some of the test equipment that is available from Sumatec Instruments and through Tesco. First is our IQA series. This is what we call the premium, or it's a high-powered unit with two 20-watt tones that are adjustable from 2 watts down all the way up to 20 watts. In some cases, you may want to reduce the power if you're going to be testing into a DAS system or systems that may have components that aren't rated for the full 20 watts. Frequency adjustability, very rugged construction. One of the nice things about it is it's a completely self-contained unit. You don't have to have a separate laptop computer for collecting data in this unit for testing on the site. You close it up, roll it to the site, open it up, and you can immediately begin testing. It has a touch screen panel PC for your interface and has onboard reporting capability. We offer this in a large variety of frequencies, not only for the U.S. frequency bands, but also for the most popular other bands around the world. The user interface is extremely simple. We understand that this is going to need to be used by installers or people that may or may not have a deep understanding of RF technology. It's got to be rugged. It's got to be something that is easy to operate and easy to interface with. So in this particular case, you can see that there's a very large number telling you what the magnitude of the PIM signal is. We can easily change the units. If you're more comfortable working in dBc versus dBm, you just touch right here on the screen, and it's going to change it over from dBm to dBc. And there's a large increasing bar, which is going to tell you whether there's a PIM problem or not. Turning on and off the system is just as simple as pressing down at the bottom left-hand corner of the screen. If you want to record that data point, you touch over here in this section, and you're able to generate data. The IQA has built-in reporting capability. It allows you to build the test report as you go. There's no post-processing required. It's going to output directly in a PDF format. Now, we also have the ability to take screenshots. So the pictures that I've shown along the way in here, where I'm showing screen views of data that have been collected off the IQA, were done by just pressing the camera icon at the bottom right-hand corner of the screen. These are the different user modes that are available with the IQA. So in the first mode, it's the time trace mode. When I was showing the tap testing results, that's where I would typically do it, is using a time trace mode. In this case, I am transmitting with 2 fixed transmit frequencies and just displaying the magnitude of IM3 versus time. So if I'm tapping on something and it's failing, I stop tapping and it goes back to passing. You can show those types of results. The second mode is a frequency sweep mode. In this particular mode, it's designed to match the type of equipment that we sell for factory testing. In factory testing, where you are broadcasting into a termination or broadcasting into an anechoic chamber and not broadcasting out into the network, you can sweep the transmit frequencies and not just look at one IM product, or excuse me, not just one IM frequency, but you can look at a range of IM frequencies. If you have an electrically long device, you may have multiple PIM sources together inside the system that could phase together and cause what appears to be a passing product appears to be a passing product pass when it's actually failing at different frequency combinations. So the frequency sweeping mode allows you to do those types of testing. Now, we caution users in the field to understand you do not use frequency sweeping when testing a site live that's into an antenna, because it means that the multiple transmit frequencies are going to be broadcast across the full operating range. You're no longer limiting it to guard band frequencies where you can control where you're transmitting. When this mode is used, you need to make sure you put a termination at the end of the line so that you're not broadcasting. Spectrum Analyzer mode is the one where I can sweep the receiver and keep the 2 transmitters on, or I can leave the transmitters off, and you can sometimes be useful to see if there's a broadband noise rise just by looking at whether looking at the receive band based on turning on the transmitter or turning off the transmitter. Now, I think time trace mode and frequency sweep mode are available from Sumatec's competitors, but I believe at this point Spectrum Analyzer mode is a unique offering by Sumatec Instruments. We also offer what we call the IMT series. This is an economy unit. It is 2 20-watt tones, so it's a high-powered test set, but it has fixed frequencies. So instead of having the sweep capability that we have with the IQA, it's 2 fixed tones. It's very, very simple to operate. You turn a knob in order to turn the power on and off, and you read off on a display what the magnitude of the PIM is. We can interface it to a laptop to be able to collect data just like you would do with the IQA model. This is our economy version. It's significantly less expensive than the IQA. It's very rugged and durable. Today, however, it's only available for United States frequencies at the 850 megahertz level. Other frequency bands are under development, but right now 850 is the only one that's currently available for the U.S. And finally, the IHA, it's a handheld version. It's a battery-operated version. It's very, very portable. It does a 2 by 2 watt test. And as I said, the industry standard for testing is 20 watts. However, a 2 watt test set is very useful for identifying spikes. I'm able to see those 30 dB spikes in tapping on a 2 watt test set just as well as I can on a 20 watt test set. So I can't use this for full site certification, but for being able to go into a site and find the locations of the PIM problems, it works perfectly fine. And this one is available both at 850 and at 1900. Where we typically see the most application for this is going to be in remote radio head sites, sites where there isn't a feeder going all the way up to tower. In that case, you're just testing just an antenna and maybe a jumper connected to it. So the fact that this is battery operated and I can carry it up the tower to do the testing is very useful. Another application for this might be for DAS systems, where I need to carry this test into remote sections of a building that AC power may not be accessible, or just physical room to get this test set may not be accessible. And it allows me to individually test splitters, tappers, or maybe even the last RF runs coming out from a remote RF unit, to be able to perform and make sure that there's no interfering causing problems directly into the DAS system. So in summary, passive intermodulation interference degrades system performance. As we showed in the slides above, previously, we were able to dramatically improve the performance of many systems by eliminating those sources that were causing interference in the system. Secondly, PIM testing and VSWR testing are both required to verify site performance and installation quality. Sweep testing does a great job of finding impedance mismatches, and PIM testing does a great job of finding defects that are going to cause interference to be generated in the system. They're both very, very different types of tests, and you need test equipment that's specific to that type of problem to be able to identify it. Which brings me back to the statement again. You really need to be doing PIM testing and VSWR testing at sites to make sure that they are ready for broadband systems such as LTE. And SummaTech Instruments, as you can see, offers a very, very broad line of products for test equipment as well as accessories to go along with it. We've been producing PIM test equipment for more than 14 years. We're very well established, have mature training programs, and we have technical support people on staff available to help at any time. So, in summary, Tesco and SummaTech are here to support you. All right, and so here's the contact information for SummaTech and Tesco. All right, Terry, at this point I'm going to hand it back to you so we can use the remaining time that we have available for answering any questions you may have.
Okay, Tom, well, thank you very much for your presentation. We have quite a few questions here, so I will read them aloud one by one, and we will go through these. First question submitted from Brian Gibson. It's more of a comment, but the comment is, the only problem I've seen with this tapping method is even factory-made connectors will fail a lot of the time.
Okay, and I would say it's not a problem with the test. It's a problem with the factory-made connector. I would say that I've seen both, to be honest. There are some, quote, factory-made cables that I've seen also fail, but I've also seen some that are rock solid. So I would put that back to the factory. There is an IEC specification for factory jumpers that uses actually this tap test or a flex test as a requirement for factory PIM testing. So the manufacturers should be expecting that their components should not only pass in a static sense, but also pass in a dynamic test.
Okay, thank you. Another next question submitted from Brian Gibson. Has any progress been made to correct the flakiness of the readings? Sometimes a more direct measurement would be RSSI, measuring the CDMA peak noise on both diversity paths, which will highlight the problem well.
Okay, well, I understand, obviously from a switch standpoint and the system telling you that there's a problem, that RSSI is an excellent way to see that there's a problem. Now, when you get out to the actual site and are trying to fix the problem, you need PIM test gear to do that. The PIM testing gear is, I'm not going to use the word flaky. It's highly sensitive. I mean, if you think about what we're doing, we're transmitting at plus 43 dBm and measuring signals down at the minus 100, minus 110 dBm. So in order to do that, it's a very, very sensitive measurement that we're conducting. I don't want to reduce the sensitivity of the test. I need to be able to see those minute problems. The fact that PIM or nonlinear junctions caused by metal-metal contacts that are just not rock solid cause these variations, it's really an indication of the actual problem. If you're seeing that I'm doing the testing and I'm seeing lots of variation during the testing, it means you have problems. Now, I will say that in some systems, you may have external interference at the frequency that you're trying to do the PIM testing at. So, for example, if I'm doing a third-order PIM test and I'm transmitting 2 tones and I'm taking this very, very narrow window receiver around, let's just use 1870 in a PCS band for an example. If there happens to be noise coming in externally at 1870, the PIM test set's going to see that. And so that's why we've added the spectrum analyzer mode, that if you suspect that you're getting strange results that don't represent what you believe is the case, and things are moving when you're not even tapping on the system, I would immediately go to the spectrum analyzer mode and take a quick peek at what's out there. Is this noise being generated, and is it being received even with my transmitters turned off?
Okay, great. Next question from Brian Gibson. I've only seen PIM on the transmit path. After roller jumpers, if RSSI spikes go away, is our only way to clearly identify a PIM problem? Or rather, it's a statement. Is our only way to clearly identify a PIM problem?
I'm not quite sure I understand the statement, but the fact that you only see it on your transmit is exactly what you would expect. Because once again, PIM is caused by your transmit signals. The high-powered tones are going to be the ones that are going to generate passive intermodulation. So when you are transmitting and receiving on a single line, that's when you're going to start seeing the passive intermodulation. And let's carry that one step further. You're going to have, from an air interface standpoint, at least 30 dB of isolation between your primary and your diversity path. If it's polarization diversity, good polarization diversity antennas these days are going to give you 30, 35 dB. If I'm using spatial diversity, I'm going to have higher. I may have 40 or 50 dB of isolation just between the 2 lines. So let's say I'm going back to the good old days where I had 2 antennas that were spatially separated, and I'm doing TX-RX on one antenna, and I'm doing receive only on the other antenna. In order to see the PIM spikes on that receive port, it would mean that I would have to generate the PIM, come out of the antenna, radiate over to the adjacent antenna, and then come down the system. And just basically due to the loss in that first wavelength of radiation combined with the isolation between the 2 ports, whatever signal I was creating is going to be at least 30, 40, 50 dB down on that receive path. Now, if you switch the lines and we're now transmitting on the other line, depending on how good the PIM problem is on the other line, the problem may follow. So once again, the transmit tones are the culprit, and I've also seen people that had a good transmit or had 2 lines going up a tower. One was low, had no nonlinear junctions on it. One of them had problems, and all you do is switch the transmit over to the line that's good, and hey, that fixes the problem sometimes.
Okay, great. Next one. Actually, we've got two questions here that are identical. The question is, can we get a copy of this PowerPoint presentation?
Yeah.
Well, we certainly are making this presentation available on our website. We have a Sumatech landing page, and it'll be sometime next week at least. We'll be able to mail out that link, and shortly thereafter, it'll be on our Sumatech landing page. So it'll be a recorded version of this webinar that will give you the audio as well as the PowerPoint slides. And that'll be a public URL link. Roger, a question from Roger. Question is, does Sumatech offer formal training?
Absolutely. Absolutely. I think I was keeping a metric of that. I think that Sumatech has done over 100 training sessions at customer locations so far this year. So, for a fee, we will come to your location and train as many people as you'd like. You can actually order that as a line item online through Tesco if you're interested. We also offer free training here at our facility in Denver for 1 day a month. We are also conducting joint seminars with Tesco where training is available there.
So work with your Tesco sales rep and find out what the next availability would be for any public session that may be scheduled, or also to come to your site and do the training at your location. And a lot of everything's expanded on, of course. In this webinar, we didn't go into the nth degree of detail probably on the PIM fundamentals and these sorts of things, but obviously in the class, when you have a good 4 hours or so, then you're going to have time to really whiteboard and really talk through things a little more in depth. Also, you get a certification with that as well. So after that course is over, then we would email you a certification. Question from Bill. How close together can you put the two fixed 20-watt signals?
There is a physical limitation by the software, which honestly I don't remember what it is. From a practical standpoint, it goes back to the slide that I mentioned that our system is currently set up to prevent you from seeing anything greater than ninth order. So it comes down to the two transmit tones that you are choosing need to, as a minimum, generate ninth order within the receive band in order to be able for the equipment to allow you to select those frequencies. Now, we put that in as a safeguard because we want to make you stop and think. You don't want to accidentally choose two frequencies that are generating PIM somewhere, completely irrelevant. We really want to drive you to do what the industry specifications say to do, which is to be testing at a third order intermod level. And as I said before, in many cases, that means that you're going to be transmitting outside of your specific band. You generally have to have a broader spacing between the two frequencies in order to make third order fall within the receive band of the test instrument. So we could get back to you on what the actual number is, but I guess it's kind of academic because ultimately you're going to need to do broader spacing of the tones in order to measure a third order. And I keep coming back to third order because, when you look at your antenna specification or you look at your cable specifications, everything in the industry has been characterized as how it performs at third order. And what I don't want to do is get into the field and be testing fifth order and be trying to make correlations. It's just much cleaner if across the board, from at the factory and in the field, we're all using the same basic test methodology in order to determine good or bad. A great example, let's say you're failing fifth order and you go back to your favorite antenna manufacturer and say, hey, IM5 is failing. You're very likely to have them come back and say, well, we certified IM3. So just to avoid all those issues, it's just much cleaner if everybody tests using the same methodology.
Next question. I think that may have been answered somewhat with a previous question, but it can't hurt to reinforce this one. What is the relationship between RSSI and PIM?
Okay, well, the relationship is that RSSI is an indication many times of PIM. Once again, if the transmit signals are hitting a PIM source and causing noise to be generated on one line, and the transmit signals on the other line are not seeing any nonlinear junctions, then you're not going to see a noise rise, and so therefore you see a differential typically, and it's usually the differential is what you're concerned with.
Okay. Next one. What model test equipment is recommended for LTE?
It really any of the systems available are fine. You know, LTE is an air interface, and the test equipment is set up based on licensed operating bands. So if someone is running LTE at AWS, then you need a test equipment that'll test in the AWS spectrum. If someone's going to run LTE at 700, then you need a test equipment that's going to be able to test at 700 megahertz. Now, there's one exception here, and that is that many of the people who are rolling out 700 megahertz systems have chosen to deploy broadband antennas and basically broadband components in the system, which means that you can use in those systems an 850 megahertz test set to test both the 700 and 800 megahertz lines, because the line itself doesn't have any frequency-dependent components that would prevent both the two transmit tones and the IM3 that you're trying to measure from passing through the system. So, in summary, you really look at what frequency bands you're trying to test, not necessarily just the air interface.
Tom, would you like to comment on the that particular LTE unit a little more that's available in the 700 megahertz?
Yeah, 700 megahertz is a little bit different. If you look at how the FCC chopped up the spectrum, you have an A, B, and C block that transmit on the high side and receive at the low side, and then you've got the upper C block, which is a very broad block that transmits at the low side and receives at the high side. Now, all of the transmits are kind of grouped together in a range between 728 and 757 megahertz. Realistically, if you're transmitting on guard band frequencies, you should be able to use either test set in order to certify that you found and eliminated the nonlinear junctions on the line. You just have to make sure that all of those frequencies I'm talking about, the two transmit zones and whichever IM product that you're measuring, all have to be able to pass through the system. If the operator has installed TMAs or filtering in the system that prevents the low end or the high end from passing, then you're going to need to select equipment designed for that particular operator's use. So it comes down to back to your operator to find out, what is your configuration? Can the test equipment that I have work in your system? And as long as both the two transmit tones and the IM3 product that you are measuring will pass through their system, then that test set can be used. If I was transmitting into just a feed cable, which is a very, very broad band transmission line, I could test it with a 1900 megahertz box, I could test it with an 850 box, I could test it with a 700 megahertz box. There's going to be slight variations in the magnitude of the PIM across those frequency bands, but when I'm finding and eliminating 60 dB PIM problems, each of those test sets will find the same problem and tell you that it's a failure.
Any additional questions on that topic, please just resubmit those if there's any more questions on that particular topic. But thank you, Tom. That was clear. The next question is, why would an antenna that is failing the return loss on an Enritsu machine, I'm assuming that's a line sweeping type of test, why would that fail on an Enritsu machine yet pass on the IQA PIM machine? The return loss on the antenna was a neg 3 dB.
Yeah, it depends on what the what type of problems is being caused. A great example is minus 3 dB return loss means that you pretty much have a broken circuit somewhere inside the antenna, because to get a minus 3 dB, it means that half of the energy is bouncing back into the receiver. And I could have a perfectly prepared coax connection It's just I just saw it off very perfectly. I make sure that there's no loose metal contacts, nothing that's going to excite PIM, and I'm not generating PIM. I'm getting a huge reflection of the two transmit tones coming back into the test set, which, by the way, is protected. It's not going to hurt the test set. But I don't generate any PIM frequencies. It's those loose metal-to-metal contacts that are the things that are going to excite passive intermod. So a complete open circuit may or may not cause PIM based on whether or not that the way that it broke is causing loose metal-metal contacts. If that circuit were a solder joint that was cracked, I would expect it to fail both tests. If it was a solder joint that cracked and completely separated, well, then you may have the instance that you've described here.
Okay, next question is from Anthony. Question is, could a one-way communication, i.e., called party hears you but you do not hear him or vice versa, be one manifestation of a system experiencing PIM problems?
Yeah, I guess that's very much possible. Let's take the example of a mobile that has reached a distance where now the PIM noise is at the same level as the mobile. You're still within the broadcast range of that sector. You're still within the planned coverage. So you're hearing communications from the BTS, but the BTS is no longer able to hear the mobile. I don't know if that answers the question or not, but yeah, that's absolutely a possibility. Now, if you're talking about a full simplex type of a system where I do a push to talk and I'm talking at one time and I can't talk and listen at the same time, in that particular case, I don't think PIM is going to be a problem.
Okay. I got a question from Bill that true with 700 megahertz as well. Bill, if you'd like to resubmit that question, now I'm not sure what you're asking there. It was probably relevant to a particular slide or a particular topic, but now question from Scott Whitney. Question is, what are the operating conditions of the test equipment? What are the future product plans?
Operating conditions. Take good care of it. That's first and foremost. The equipment is designed to handle pretty high shock, actually. As part of our testing, we do not only drop testing, but also put it on a vibration table and vibrate it. We typically recommend that the operating temperature be above freezing, so that if you are at above zero, there's some circuits in there that really don't like being soaked at a minus 20 degrees Celsius or something like that. So from an operation standpoint, my recommendation is don't store it in the truck overnight. You're much better off storing it indoors and going out and testing. Once you're testing, it has its own self-heating, so it's really not a problem in that case. On the other end of that side, the equipment is going to shut itself off when the internal amplifiers reach, or the internal amplifier casing reaches 70 degrees centigrade, which is approximately 150 degrees Fahrenheit. So I have seen cases where when people are testing in the desert, it reaches that thermal overload, and they have to take the unit back into their truck in the air conditioning, cool it off a little bit, and then continue testing. So those are kind of the limits. The limits are primarily related to temperature range, vibration shock, and then also, these things are not designed to be used in the pouring down rain. The units themselves are sealed so that if it's closed, you're not going to get water pouring into the unit. But when it's open and operating, it's not designed to be used in rain. Okay, now that was, and Terry, remind me, that was the first part of the question. What was the second part? The future plans. From a future development standpoint, we are always trying to expand our product offering to cover things like new frequency bands. We also are very sensitive to the feedback that we receive from customers. So we are listening to concerns they have, like, hey, I don't like carrying around a 50-pound box. Can you make it lighter? We are looking at technologies in the future that allow us to do things like that. There's also desires to say, hey, this tap testing I'd like to have something that gives me the same functionality as my distance default on a sweep gear. So we're working on things like that to make it potentially easier to find faults that are out there in the system. So we have a very strong and active R&D department, and as we said from the beginning, Summitech, this is our focus, this is our business. So, if we're not designing the next generation of product, then somebody else is, and we don't want to, be the guys lagging in this industry.
Great. Another question from Neil. Does the PIM test equipment require yearly calibration?
That's a very good question, and I have to take the party line, which says, oh, yes, of course. And let me give you some practical experience there. I've been out in the field. We've done some recent software upgrades, and as a service, we've stopped by customers who had the equipment and and upgrade their software at no charge. In so doing, I've come across a lot of pieces of equipment that are technically out of calibration. Now, many of these had only seen light usage, and in testing them, the quote calibration, meaning how accurately it was measuring a known PIM source, they were spot on. So from a does it need annual calibration? I'm going to come back and say it really depends on how heavily that unit is being used. The more vibration it's seeing, the more time in the field, those are things that are going to impact how long it's going to hold on to a solid calibration. Now, having said that, the first step you always do before performing a test is check the calibration. There's nothing you do to change it, but you put a low PIM source on it and make sure it's still measuring low, and you put a known high PIM source on and verify that it's measuring high. As long as those two tests are within spec, the unit is still operating correctly. Now, one other feature of our annual calibration is that we service the unit. So not only are we adjusting the parameters that are impacting the measured result, but we go in and vacuum out all the bugs and spiders and dirt and everything else that's built up on your amplifiers. And it tends to allow those amplifiers to run cooler. What that's going to do for you is it means that you're going to have a longer reliability on that unit. So I highly recommend sticking to an annual calibration cycle, especially if you're using this equipment day in, day out in the types of environments that we know you're working in.
And another question, well, back to that question for one second is you may want to expand just real quick on what comes in the accessories kit for the calibration, the known the source and load.
Yeah, the standard accessory kit that we ship is basically everything you need to perform the test when you're testing into either a Type N system or a 716 DIN system. So we have multiple test leads to connect between the test equipment and test to the site that you're testing. And we have all the adapters necessary for you to be able to adapt not only the test lead, but also the terminations that we provide to be able to adapt into either a 716 DIN or a Type N system. So those are the basic components. We supply the wrenches, we supply a torque wrench, we supply a cleaning kit. When you got to keep your connectors clean. If you get those metal flakes inside your test equipment, all of a sudden you're measuring terrible PIM just from the metal flakes that shaped off inside your connector. So cleaning your connections periodically is important, and the cleaning kit is part of that. And as I mentioned, the low PIM termination and the high PIM termination are available standard with the kit. I'll recommend to anybody, if you're buying a kit, you really should get an extra termination because many times you may want to be doing testing of jumpers at the bottom of the tower while the guy climbing the tower may have the termination up at the top for putting at the end of the cable. So it's generally useful to have extra terminations available.
question, Ryan, is, are you able to test in both guard bands? And it may help for the audience as to define real quick what a guard band is.
Both in guard bands. I think the question is, can both frequencies be in guard bands? Absolutely. When we ship the units from the factory, we ship them with both tones set in guard band because about half of the units we sell are going to third-party operators or installers or people who none of them technically own the licenses. So we want to make sure that when they turn on the unit, they're not broadcasting in somebody else's spectrum. So yes, absolutely, both frequencies can. And honestly, when people ask me what frequency should I use, I generally say leave it where it is, unless there's some overriding reason that you want to change the frequencies on that unit.
Good. So basically, it keeps the default setting is it allows testers to not test within the live traffic bandwidth, basically, not to step on any live bandwidth. Question from Neil: are the Enritsu terminations compatible with your PIM testing solutions?
That's a great question. Absolutely not. The sweep test loads are very, very precise loads, but they are not able to handle the power that we're transmitting with a PIM test set. And what happens is if you still have the Enritsu load at the end of the line and you turn on the transmitters, you're going to fry that load instantly. So it's an instant $700 mistake. So be very careful. We recommend that when you're communicating at a site, that you and whoever's at the top of the tower have very, very clear method of communication on things like, I'm turning the power on and the RF power is off, and don't just say put the load at the end of the line, because the guy at the other end doesn't know which load you mean. So, make sure you say clearly, put the low PIM load on the end of the line so that you don't make that mistake.
Good. If you could make out. Bear with me just a moment. Question from Bill is, why do you ship with the units in the guard bands, set to transmit in the guard bands? I think we already answered that, and that may have been asked before you went over that.
Yeah. Once again, we ship them in transmit because if someone buys a PCS block or a PCS unit, I want to make sure that they're not transmitting in any of the A, D, B, E, F, or C license holder spectrum. So I want to make sure that when it leaves here, we're transmitting at guard band frequencies, which means that we're not going to cause interference on anybody's network.
Let me read this one here. A little bit longer of a question here from John. I have an issue with my 1900 IQA PIM machine. After my tech PIM tests a cell site, when they try to save the report on the D file, the report will not save. It says the directory file cannot be created. What could be the issue?
Good question. I would say as a first workaround, save it directly to the USB ports. We really honestly designed the primary method of saving to be to put it onto a USB stick, either on one of the two drives on the unit. Now, theoretically, if you fill the D drive, which would be kind of hard to do, I think we have allocated somewhere around 250 megabytes of space available for saving reports. If you filled it, then it's going to not let you do that. If there's some corruption that has occurred on the D drive, that potentially also may limit the ability to save directly to the D drive. I have seen that before, and what I've done to fix that is go in and reformat the D drive, clean off whatever the corruption was, and then it clears it up. Now, that's something that we lock you out from being able to do that. We don't want you to be able to accidentally go in and reformat your drives. But if you contact customer service at Sumatech, we'd be happy to help you get your equipment back up to where it's able to be saving data to the D drive.
I think that's a good point there. The USB drive is, it seems like it's plug and play. When I plug in the USB, it auto recognizes it on the system, and it's all automatically available to be saved to. So that could be an easy remedy. Next question from Bill. Do you need to transmit in 800 megahertz to test 700 megahertz lower A, B, or C blocks?
Now, once again, we use two frequencies in order to generate tones that are going to excite PIM problems. And like I said before, the only requirements on what frequencies I'm doing is that they must be able to pass through the system with a good return loss. My target is I want to see at least a 10 dB return loss into whatever I'm testing before I'm going to fire energy into it. With a 10 dB return loss, that means that only 10% of the energy is bouncing back and 90% is passing through. So at least a 10 dB return loss. I want to make sure that I also have a good return loss at the frequency that the IM frequency is being measured at. And as long as those requirements are met, and as long as I'm broadcasting in spectrum where I'm not going to cause interference, those are really the requirements. If there is a PIM problem, a nonlinear junction, you will be able to find and eliminate the nonlinear junction. Because at the end of the day, nonlinear junction removal is really what we're here to do. We're trying to eliminate those sources so that it's fixing PIM problems across a very, very broad range of frequencies.
Excellent. And somebody, one more is a comment, and somebody commented that it's a great feature to have adjustable frequencies. Would you like to expand anything more? And just that, some of the, the test equipment comes with set in the guard bands, but that there is adjustable frequencies that may have some benefit to someone that's trying to do something in particular.
Yeah, I play with the frequencies all the time. If I'm going to a cell site and I'm just working to fix PIM problems, I usually don't mess with it. I usually leave it alone. However, in the things that I'm doing, like you saw the slide where I intentionally put the transmit tones on the PCS-A block so that I could make many different frequencies show up in the other receive bands. That's an example where I was able to change the frequencies and be able to adjust it. Another instance is, let's say for whatever reason I'm testing on a site and there happens to be interference at the IM3 frequency that my fixed tones are at. And if 5 megahertz away it's clear, I could change to a different guard band frequency to move my IM product over to a clear frequency and then continue testing. So that's really the only time that I would recommend ever changing frequencies. If there's some scientific thing that you're doing, or if there's interference at the IM3 frequency that you're actually trying to measure at.
Thank you. Next question from Bill is, what is the minimum spacing of the frequencies to get the spec dynamic range? Specific dynamic range.
Well, I think we've already answered that. It's not a dynamic range issue with regard to the receive. It's really a just do the math of how do I get 3 times frequency 1 minus 2 times frequency 2, or whatever the math is. How do I make that combination physically fall within the receive band of the system? Yeah. So that's what's going to determine the spacing between your transmits, is to get them far enough apart so that the mathematical combination moves far enough away from the 2 transmit frequencies.
Okay. not getting any more. That appears to be all the questions. If no one has any more questions, anything else you see on your end, Tom, that needs to be addressed?
No, I'm looking at the ones I've seen. I think we've got them all.
Okay, great.
I have to say, there's been a lot of repeats of, how do I get the presentation? How much does the equipment cost? And I'm going to decline in this forum of talking price and say, contact your Tesco sales representative. They'll be happy to help you with that. Now, there is a new one from Bill that says, what is the closest spacing as you've used? The closest spacing that I have used is I've gone into like I said, the PCS band and put it on just the two band edges at PCS. And so that was, 15 megahertz spacing is what I've done. I can continue it down to the limit that to which I can actually measure the higher order product that's created. Our transmit tones that we use are 5 kilohertz tones. So from a practical standpoint, there is a fixed number. Like I said, there is a number that I can't go any narrower just because of the performance of the system. But from a practical standpoint, I've never in the field ever approached that.
Good. One comment, though, or one thing you may want to expand on, someone's asking, how much the gear costs. Maybe it makes sense here, just in this venue, just to explain or maybe reinforce the difference between the handheld IHA, which is a lower cost tester that's very portable and you can bring way up the tower, versus a full-blown IQA.
Yeah, from a rough standpoint, the price of an IHA is a quarter to 1/5 the cost of a full-blown IQA. You get a lot more capability with the IQA. One is I've got 20-watt transmitters plus all of the reporting capability, et cetera. So those are the things I get with the IQA. I get the touchscreen interface, full reporting, 20-watt transmit tones. And with the handheld, probably the biggest difference is, number one, on the plus side, it's battery operated and highly portable. On the minus side, there is no reporting. It's really intended as a good, bad, where's the fault kind of a unit. So if you're buying a piece of equipment with the intention to use it for site certification, you really need to get a unit that's going to be able to output data and give you that as a result. You also need a unit that's going to be able to test at 20 watts, because that's what every operator is using as their pass-fail criteria. So, if you're using it for site certification, you need to get something that's 20 watts, whether it be the IMT Economy or whether it be the IQA Premium. Now, if you're a technician and you want to just be able to have something that's small and lightweight in your kit, and you're at a site and you think, I think I may have a problem here, and you think, let's just say you're in the shelter and you think, I just wonder if my jumper between the diplexer and the main feed is good. You'll be able to determine that, by spiking those joints to determine if you have something bad. You can use it as a tool to say, hey, there's problems here. I know I need to get somebody back in, someone with a power crew or something else. So from an engineering perspective and a troubleshooting perspective, the IHA is a great piece of gear. And it's designed to be very affordable and lightweight. So I don't know if that covers that or not, Terry.
That's good. That's exactly what I was looking for. I think that might help clarify out in the audience what the differences are, and that there is a lower cost go no go kind of a unit versus a real 20-watt IQA version.
Yeah, and there's a question from Neil. I'll try to address this. Neil asks, since the test equipment is so expensive, if newer models come along, can you trade it in? I can't guarantee that. If you've bought it and have used it for 2 years and well more than paid for it, what's the trade-in value on that? I'm not sure. I think we're in this business for the long haul, and our objective is to make sure that we're not creating enemies. I don't want to sell you something just because I have it in inventory, and 2 days later you find out that there's some whiz-bang new version. We try to be as upfront as possible when we're coming out with new versions and give people as much notice as possible. And as it's going to happen. So as we come across those barriers of we may be coming out with something that's radically different, we're going to try to make sure that we're giving you that information up front so that you can make a good business decision.
Yeah, and Tesco does offer a trade-in program, and basically customers work with our sales reps, and we take down in the information. We find out what features and what the serial number is and that sort of thing, and then we give we come back in a day or two and give somewhat of a verbal estimate, and then we wait for the unit to be sent in before we can really appraise it. So we can't guarantee 100% trade-in at all times, but we do a lot of trade-ins to help people in the test equipment business. So when they're in the market for test equipment and they have an older piece out there, hey, it can add up. It just depends on what the age of the equipment is, what the condition of it is, and what the features are on it, and what the demand is on the used market. That obviously when it gets resold. So we absolutely will work with customers on trade-ins, and also we have another service that a lot of folks are using with Tesco is lease to own. So if you're having cash flow issues on purchasing a piece of test equipment, then we can certainly work with you on lease to own terms or other credit terms. Waiting to see if any other questions came up. I'm not seeing any on my end. Tom?
No, I think we've cleared them all out.
Great. Okay. Well, if there are no more questions, then this concludes our webinar for today, and we want to thank everyone for joining.